Well, hello, and we're going to look at just a couple of tutorial problems for Chapter 3, Section 1. We're just going to do the first 5 here of the tutorial problems. Again, you might like to try having a go at these yourself before looking at the worked solutions. So the first one's just 3 sort of related ideas. So the first one, we want to show that the product of the divisors of n is equal to n to the torr of n on 2. Torr of n is the number of divisors of n over 2. The second part is to use the arithmogeometric inequality to prove that sigma of n on torr of n is bigger or equal to the product of the divisors of n, where each of the divisors is to the power 1 over torr of n. And the third bit is to deduce that from this one that sigma of n on torr of n is at least n to the half. Just a few little connections between sigma, the sum of the divisors, and torr of n, the number of divisors. So to solve the first one, we're asked to show that the product of the divisors of n is equal to n to the torr of n on 2, torr of n being the number of divisors. Well, so I'll give this thing a name, call it P, to be the sum of the divisors of n, the product of the divisors of n. And an old trick, of course, is once you've got a product or sum of divisors, you can rewrite this taking the order backwards. So instead of taking the divisors in order of n, then you take the divisors you take n over the divisor to get the cofactor, and you take the product back the other way. So I'm going to take this p and square it. I'm going to write one of the p's as this, and the second p is to take this product, which is exactly the same as this, it's just we're taking the order backwards. These are the cofactors. And now it's simple, because when you can now multiply the two products together, then the d's cancel. And then we simply get a product, we get n times the product 1, where d divides n. So each of these, for each divisor, we're going to get n, and there are torr of n divisors. So we're going to get n to the power torr of n, and that was p squared, so you can take the square root. This is a nice little formula here, because it immediately tells me, we know this product's got to be an integer, so it tells me in particular that if torr of n happens to be odd, then n would have to be a square to make this an integer. And we'll come back to that in a later problem, in fact. When is torr of n an odd number? Well, if it is odd, this tells me that n has to be a square. The second part was to show that the quotient of sigma n on torr of n is at least this product. And again, and it says use the arithmogeometric inequality, which simply says this, that if the ANs are all positive, so if you take the average of these n positive numbers, then it's bigger or equal to the geometric mean, that is 1 over n. The product of them to the power 1 over n. So I take sigma of n to be the sum over the divisors. Now using this here, the ai are going to be these divisors, and the n is going to be the number of different n, of course. The n in the formula here is the number of factors, which is torr of n. So I can multiply this up to here. So this is torr of n times, I simply take the product of the divisors to the power 1 over how many divisors there are, that's torr of n. And that's it. The result then follows just by division. So putting that together, we want to prove that this quotient's at least root n. We've just proven that this quotient is bigger or equal to this, and we've just shown that this product in here, from part A, we've shown that this is n to the torr of n. So we get n to the torr of n times torr of n over 2. So we get n to the power torr of n over 2 times 1 over tor of n, which gives me just n to the half by part A. And that's the end of that question. Problem number 2 was again to prove a little bound on tor of n, to show that for n is bigger than 1, the number of divisors of n has to be less or equal to twice the square root of n. So I'll do a little quick proof of that one. So I want to prove tor of n is less or equal to 2 root n for n bigger than 1. So if we take our n, if we can factorise it as k times l, then either k is less than root n or l is less or equal to root n. They can't both be bigger than root n, otherwise their product would be bigger than n, which is impossible. So we just observe that fact. We suppose now that the divisors of n are a1 up to a sub tor of n, because there are tor of n divisors, and put them in increasing order. Then by what we said above here, at least half of these numbers must be less than or equal to root n. Okay, so if we take tor of n on 2, that is the index of half, that's half the number of divisors. So the divisor number has to be less or equal to the divisor itself. So tor of n on 2 is less or equal to a to the ceiling of tor of n on 2, in the case when this is not an integer, which can happen. And then we've just shown that, we've just said that at least half of these, so in particular this number, have to be less or equal to the root n, so that's less than root n, and then multiply across gets me the result. Question 3 asks us to prove that this sum of the reciprocals of the divisors of n is equal to sigma of n on n, and we want to know in particular, if n is a perfect number, what is the value of this sum. We then want to show that if m is a factor of n, then sigma n over n is bigger or equal to sigma of m over m, when m is a factor of n, and hence deduce that no proper factor of a perfect number can be perfect. So a little bit there on perfect numbers. So firstly, again, we use this little trick of summing backwards. So we take S to be the sum of the divisors, sum of 1 over the divisors, where we run through the divisors of n. And all we do is we can say, well, 1 over a divisor is the same as a divisor over n, but summing backwards. So for each of these factors, we look at the cofactor. And of course, then I can take the 1 over n out of the sum, and I simply get sigma d divides n of d. And of course, that by definition, that's just the sum of the divisors. And that's the result. Now the interesting thing is, if S is perfect, then sigma of n is 2n. And in that case, if I plug 2n into here, we're going to get sigma of the reciprocals of the divisors of a perfect number adds up to 2. By the way, this is an interesting, one of the many ways one can generalize perfect numbers is to define perfect numbers of or pseudo-perfect numbers, or whatever name you want to give it, by choosing your n so that this sum is not 2 anymore, but say 3, or what other values can it be? And you can define pseudo-perfect numbers by simply changing this sum here. The second part says if m is a factor of n, then we've already shown that sigma n over n is this sum of the reciprocals of the divisors. Now m is a factor of n, so m is less than or equal to n, so this sum is bigger or equal to the summing 1 over d, where d runs through the factors of m, and then by definition this is sigma m over m, which gets the desired result. Finally then, if m is a proper factor of n, if m is a proper factor of n, then we have this result here, if it's a proper factor. Now if n is perfect, then that means sigma of m over 2, we know that this thing is equal to 2 if n is perfect. So if m is a proper factor of that, this sum must be less than 2. And that means m can't be perfect, because if m is a perfect number, this sum is exactly equal to 2. For question 4, we want to, part A, we let n be a number of the form 12k plus 2, and we're going to suppose that 6k plus 1 and 4k plus 1 with the same k are both prime. So, for example, if k was 1, so this would be 14, then 7 and 5 are both prime, so this can happen. We want to prove then that Tor of n is equal to, in this scenario, Tor of n is equal to Tor of n plus 1. Now, tantalise you a bit, it's an unsolved problem to show, I believe, that there are infinitely many such n. There are infinitely many n such that Tor of n equals Tor of n plus 1. Because we don't know that there are infinitely many numbers of this shape where both of these are prime. And part B is to show that prove that Tor of n is odd if and only if n is a square. I mentioned before we saw that if this is odd, n had to be a square. Well, now we're going to do the more general proof here. So for question 4, that's a nice just little example of playing with Tor of n. So firstly, if n has this shape, it's 12k plus 2, and I can factor a 2 out of that. So Tor of n then is just, these are relatively prime, so Tor of 2 is Tor of 6k plus 1. Now Tor of 2 is 2. This number was assumed to be prime, so it's only got 2 factors, so that's equal to 4. Now n plus 1 is 12k plus 3, and you can factor a 3 out of that, so we get 3 into 4k plus 1. And so Tor of n plus 1 is by multiplicative nature of Tor. These are relatively prime. This is Tor of 3 times Tor of 4k plus 1. Tor of 3 is 2. This again was assumed to be prime, so this only has 2 factors. So 2 times 2 is again 4, and so these two numbers are the same. Part B, I'm going to assume n is a square. So if n is a square, then its prime factorisation must look something like that, where the pi's are all prime and the alpha i's, that's alpha 1 there, are all non-negative integers. And then Tor of n then, by definition, or by the formula for this, is just 1 plus this number all the way up to 1 plus this number, but these are all odd, and a product of odd numbers is odd. So that says if n is square, then Tor of n is odd. And we saw before that if Tor of n is odd, it's got to be a square, but here's just the other way. It's a simpler way of doing it. So if Tor of n is odd, and there's the prime factorisation, then that tells me that Tor of n is just 1 plus alpha 1 up to 1 plus alpha r. And this number is supposed to be odd. So that means all of the factors in the product has to be odd, and that means each of these factors, each of these numbers has to be even. So alpha I is even, and that means n must be a square. Final one here, question 5 for this section is, this is another extension here. So we've got sigma to the k of n denotes the sum of the kth powers of the divisors of n. And we want to find a formula for that one. Now I'm not going to, I'm just going to tell you the answer for that one, because it's, you do it exactly the same as we did in the other recording. So there's the prime factorisation of our n, and sigma to the k of n is the sum of the kth power of the divisors of n, so it's just that sum, and then it equals this thing here. These again come from geometric series, so you simply write down what this must look like as a product of prime powers which form a geometric series, and you sum each of the geometric series and get the general formula here. So it's done in exactly the same way as we did in the recording for section 3 for chapter 3 section 1, and there are the couple of tutorial problems for that section.